Bismillahirrahmanirrahim. My name is Dr. Amber Rashid, and today my topic of presentation is probability introduction and with the application of multiplication rule and the addition rule under supervision of Professor Dr. Zaira Afzal. I will be presenting. In this presentation, there will be a brief introduction to probability and its basics, and what are the types of probabilities with application of probability, multiplication rule, and addition rule. We will not discuss the types in detail, but main focus would be on addition and multiplication rule. So at the end of the presentation, the participants would be able to describe the probability, its basic rules regarding addition and multiplication techniques with examples, solved examples. So coming to the probability, so probabilities in very simple terms, probability is simply how likely something is to happen in near future. In probability, we are talking about the future, not the past. And whenever we are unsure about the outcome of an event, we can talk about the probability of certain outcomes, how likely they are, and how likely they would occur simultaneously or individually. And the idea of probability is based on observation, and probability describes what happens over many trials. So definition of probability in technical terms is probability is the measure of how likely it is some event will occur. And it is expressed as a number expressing the ratio of favorable cases to the number or or the outcomes possible. So the formula here shows that the number of favorable outcomes and the number of possible outcomes. So this is the general formula for the probability. So the best example. So the best example for understanding the probability from with the simplest example is the flipping of the coin. So whenever we are using a coin, there are two possibilities and there are two outcomes. Either it's a heads or a tails. So what's the probability of a coin landing on heads? So when we are thinking about the probability, then that one thing comes in our mind that there's a half chance of having heads and half chance of having tails. So the probability when we have the favorable outcome is heads. So it comes in the numerator and it's 1. And the possible outcomes would be 2, that are heads and tails. So it will come in the denominator and it would be 2. So 1 by 2, it's 0.5 or 50%. And normally we show it with whenever we are using such a scenario where there are two outcomes only. So we use this type of probability tree where there is half and half chance of both the favorable outcomes like heads and tail. So a tree diagram actually helps to organize and visualize the different possible outcomes. If we have more than one possible outcome, as in case we are using two coins, the example that is coming in the next slides, so we can easily visualize the possible outcomes in a very simple way. So branches and ends of the tree are the two main positions, the branches and the ends. And the tree diagrams are used to figure out one to multiply and one to add. And this also helps us for this as well. So in this case, it's a simple tree diagram. So there's some examples of calculating the probability. Like for the first example, you can see that there are total 6 pillows in the bed. 3 are red, 2 are yellow, 1 is blue. So total we have 6 pillows. What is the probability of picking a yellow pillow? Since we have the favorable outcomes that is 2 pillows, so we have favorable outcome of 2, and we total have chances. Total pillows are 6, so it will come in the denominator, the total outcomes. So hence the answer would be 1 by 3. Secondly, in the second example, you can see that if there is a container colored bottles, red, blue, green, orange. So some of the bottles are picked out and displaced, and a person did it 1,000 times and got the following results. And after these following results, the blue bottles were 300, the red bottles were 200, the green bottles were 450, and the orange bottles were 50. So what is the probability that this person would pick the green bottles? So we would add all these outcomes, the total outcomes that would come in the denominator, and the numerator would be the favorable outcome for the green bottle, that is 450. So the answer is simple, that is 0.45, or you can also use a ratio. And if there are 100 bottles in the container, then how many of them are likely to be green? So if it implies that 450 out of 1,000 are green, then out of 100 that would be 45 green. And then when we would calculate it from with using 45. So this is simple mathematics. So whenever we are considering the all possible outcomes of an experiment, like I have explained in form of when we are using two coins, the two coins are tossed. Then the space, either in the form of this 2 by 2 table or contingency table, or in the form of a tree diagram, the whole of this part is known as a sample space, showing all possible outcomes in an experiment. So keep this in mind, the term sample space. So in the sample space, we can have these possibilities. On both coins, we can have heads and heads, heads and tails, tails and heads, and both tails. So these are the four possible outcomes we can have when we are flipping two coins. So this is an example from the book. So here, similar to the previous one, there has been a tree diagram and the 2 by 2 table. And we normally use this 2 by 2 table in many of the study designs we apply when we are doing an original research or an experiment or a cross-sectional study to calculate various morbidity measures and odds ratio and risk factors. So considering this following, as I have shown, you have seen in the previous picture that there are four possible outcomes. So whenever we are flipping two coins, the chances of having two heads is 1 by 4. At least one heads 3 by 4. At least no heads is 1 by 4 because of tails and tails, and similarly like this. So we can divide these in the probability of events. So now coming to another concept, there are some events that are called mutually exclusive and some are complementary events. The mutually exclusive events are those events that cannot occur simultaneously, and not specifically, they are not specifically only the two outcomes, there can be more than one outcome, and both events don't have any common element. That will be explained later on. It's just to differentiate the two events. Likewise, the complementary events, when an event occurs if and only the other does not occur, and occurs only when there are two outcomes, and if one or the other must occur, but they can never occur together, meaning there is no alternative. And the two complementary events have some rules. I will explain this part later on. But generally speaking, if you see that this is depicting that whenever we are using mutually exclusive events that are not related and that cannot occur simultaneously, then we see that the these events would not be having a negative value. It would be 0 and 1 always. The sum of all the mutually exclusive events would be equal to 1. And if we are calculating the probability of not having that event, then it would be 1 minus this probability of having an event. These are the three properties that you must remember. Then coming to the two complementary events. The two complementary events, one is the counterpart of the other one. If this happens and if this don't happen, then the sum would be equal to 1. And if we are having the probability of not having that event, then it would be 1 minus that event. So explaining it with the example, you are rolling a dice. So there are 6 outcomes, possible outcomes. You have 1, 2, 3, 4, 5, 6 on the dice. So there are possible 6 outcomes. And what is the probability of rolling an what is the probability of rolling a particular number? For example, you can say the even numbers. So the probability of having the even numbers would be um, 3 by 6. There are 3 even numbers, 2, 4, and 6. So the probability of 2 or 3 would be 2 by 6, and the probability greater than 3 would be 3 by 6. 3, 4, 5, 6. So there would be 3 by 6. So the mutually exclusive events cannot happen simultaneously, and this I have already explained. And therefore, the complementary events, as I have already told, that they are complementing each other. One will occur and one will not occur. There is no alternative for that. So the examples is that it will rain or not rain. The students will pass the exam or not pass the exams. And you will win a lottery and you don't win a lottery. So basically the complement of an event occurring in the exact opposite, that the probability of it is not occurring. So these are complementing each other. And there are some non-mutually exclusive events. These are the events that can happen at the same time. There is slight bit of overlapping when we are using the Venn diagrams and the basic concepts of addition and multiplication rules, explaining later on. So, for example, driving and listening to the radio, even numbers and prime numbers on a dice, losing a game and scoring, or running and sweating. So, non-mutually exclusive events can make calculations of probability more complex. Here you can see that these two events are mutually exclusive events, not related to each other and cannot happen simultaneously. However, the non-mutually exclusive events can occur simultaneously, and when they occur, they have some overlapping. And for this, the rules in multiplication and addition, the formulas changes for such events and for mutually exclusive events. I hope you are getting my point, because these are the basics, and these basics will develop your multiplication and addition rule. So quickly going through the slide of application. So this probability has a wide application and can be used in our daily life, like choosing a card from the deck, flipping a coin, throwing a dice in the air, pulling the red ball out of the bucket of red and white ball. So this is the real life examples. Other applications is used for the risk assessment and modeling, weather forecasting and predicting weather changes, probability of team winning in sports based on players and strength of the team, and in the share market, chances of getting the hike of the share prices. So these are all the applications of where we can apply probability. So now coming to the addition rule. So whenever we are considering two events, and the addition rule is being considered, so we will state that the probability of two events is the sum of the probabilities of two events. That will happen. Here we are minusing the probability of both A, and this is this inverted, this U-shaped symbol is OR, and this inverted U is AND. So remember this one. So the probability of A event, probability of B event minus probability of A and B event. This type of situation or this formula would be used when the events are non-mutually exclusive and when there is a slight bit of overlapping, like this one on the left side. So we would, to avoid the duplication of this part, event A and probability of event A and B, we will be minusing this portion of events of A and B both probability, so that we avoid duplication and overexpression of our results. So this is for the non-mutually exclusive. Here we can see that any outcome in A, any outcome in B, and any outcome in both A and B. So this applies in the addition. So this is an example. It's a very simple example where I would like to clarify here, if we are using mutually non-exclusive events, like there is no possibility that both the events could occur simultaneously, then then the probability of both the events occurring simultaneously would be 0. So here we will not minus any of the probabilities, we'll only minus 0, or we would not show the minus sign in that equation. Likewise in this example, that when two events A and B are mutually exclusive, the probability that A or B will occur in is the sum of probabilities of each events. Okay? So let us use this addition rule to find the probability of experiment 1. So experiment 1 is a single-sided dice is rolled, and what is the probability of rolling 2 or 5? So probability of rolling 2 is 1 by 6, and the probability of rolling 5 is also 1 by 6. So in this case, we would be adding the probabilities, and we will get 1 by 3. Since the events are mutually exclusive, so nothing will be subtracted from the equation. Second example is for the mutually non-exclusive events. That when two events A and B are non-mutually exclusive, the probability that A and B will occur, here we will minus the probabilities of both occurring simultaneously. So for the example, in a maths class, there are 30 students. 17 are boys, 13 are girls. And on a unit test, 4 boys and 5 girls made grade A. Now, if a student is chosen random, what is the probability that we will choose a girl or an A? So for this, we will use the formula. We will use a probability of choosing a girl. Total 30 students, we have 13 girls. So the favorable outcome out of all the outcomes would be 13 over 30. That would be 13 over 30. We will add 9 by 30, where these are all those who got A grades, 4 boys and 5 girls. A grade. So that would be the probability of getting an A is 9 by 30. And when we are also considering the fact that there is some kind of overlapping, both the girls can have A grade out of all the class. So we will only minus these 5 girls that have already got grade A from out of 30, and we will get the answer 17 by 30. I hope you get my point. So this is the example of how you get kings or jacks from the normal deck of cards. So king or jack. So there is a probability that we have 4 kings out of 52 cards and 4 jacks out of 52 cards. And since there are no other kings and jacks, and you can only have either a king or a jack, so there are mutually exclusive events. So we are minusing nothing from that. And it's only 8 by 52 and 2 by 13 is the answer. Likewise, if we are using some kind of event that is mutually non-exclusive, like a bucket of, we are having 3 scoops of chocolate, 4 scoops of vanilla, 3 scoops of butterscotch. So what is the probability that randomly selected ice creams you will taste chocolate or vanilla? So we will have the probability of chocolate 3 out of 10. There are total 10 scoops, 3, 4, and 3. It's equals to 10. So there is 3 by 10, 4 by 10, and since there is no other chance of, sorry, I confused it with the mutually non-exclusive. It is mutually exclusive, and we are minusing nothing from that, so it is 7 by 10. My mistake. So summary of the addition rule is that to find the probability of event A or B, we must first determine whether the events are mutually exclusive or non-exclusive. Then we apply the probable rule. So for the mutually exclusive, we will use the probability of only adding the sum of probabilities of each event. Whereas when the events are non-mutually exclusive, then there would be some overlapping of these events, and the probability that A or B will occur in is the sum of probability of the events minus the probability of that overlap. So this was the summary. Now coming to the multiplication rule. So for the multiplication rule, you have to understand the difference between the mutually exclusive and the independent events. So the key difference between an independent event and mutually exclusive event. Like if two events A and B are mutually exclusive, they cannot happen together. That I've already told you. But if two events A and B are independent, if they are not related. And mutually exclusive events are independent of each other, just like the independent events. So the mutually exclusive events can be related, but they cannot occur simultaneously. However, the independent events are totally independent and not at all related to them, not at all related to each other. Hence, we are calling them independent. And all the mutually exclusive events are independent events. So this is the minor difference. Like the outcome of rolling a dice are mutually exclusive events. They are related to each other, but they cannot occur simultaneously. Like you can either get a 5 or a 6. but you can never get 5 and 6 at the same time. So outcomes of rolling our dice 2 times are independent events. So these are not related, but it is there are independent events, and outcome of rolling a dice 2 times, it's an example for an independent event. And there are some also dependent events, like events are dependent if the outcomes of one event affects the outcome of the another. And in probability, dependent events are usually real life events, like Sam scored well in maths just because he studied. These events are interrelated, and they affect and the one event affects the outcomes of the another effect. If you are not paying the bills over the time on the time and having your power cut off. So these are the dependent events. Now we will start the multiplication rule. So according to the multiplication rule of probability, the probability of occurrence of both the events is equal to the product of the probability of B occurring and the conditional probability that the event A occurring given that that event B occurs. This is a difficult point. I will try to explain it in very simple terms. So keeping it very simple, whenever we are considering two events and we are using the product, so we will calculate the probability of B and the conditional probability of A, because if B is conditioned with A, and although A and B are two independent events in experiment, uh, like I will explain it in mutually exclusive and non-exclusive. So coming, if they are mutually exclusive, likewise in addition rule, we only added the probabilities of both the events. Here we will have a product of both the events, probability of A, probability of B. In mutually exclusive events, that are two independent events. But if they are two dependent events or mutually non-exclusive events, then we will use this conditional probability, or we will multiply it with the combined probability of having both the events. So I think this is in the similar pattern. The difference is just there is a product, and in addition rule there was addition. So these are the multiplication rules. So it is an example that there are 20 red balls and 10 blue balls, and the two balls are drawn from a bag, one after the other, without replacement. So what is the probability that both the balls are red? So let's A and B denote the events. Denote the events that the first and the second balls are drawn are red. So we have to find the probability. So the probability A, probability red drawn, is 20 by 30. Now only 19 balls are left. I think this example is quite difficult to understand. I will skip to the next part. This one is the simpler one. So this one is a simpler one. That Christy has a bag of candies. And in the bag there are 5 red colors, 3 orange colors, 8 green colors. She takes one candy, records its color, and puts it back in the bag. She then draws another candy. What is the probability that out of green candy followed by a red candy? So green and R. So there will be we have to see the probability of green. So we will have the probability of green cross product probability of red given green. So that would be 8 out of 16 would be the green, and the probability of red given with green is 5 by 16, as you have 5 by 16. So this is a simple product and we get 5 by 32. Similarly, if you are considering the other situation, then the two cards from the standard deck, what is the probability that the first card is the queen and the second card is the jack? So in this case, we will use queen or jack. Here we will use a probability of queen, and we have 4 queens out of 52 cards, so it will be 4 out of 52. And here we have the probability of q out of probability of conditional j with q. So we have removed one q, so it will be out of 51. This all getting so complex. Otherwise we can get 4 out of 663. So coming to the multiplication rule explains the condition between two events. For two events A and B associated with sample space, S, A, and B denotes. Sample space meaning all the possible outcomes. We are considering all the possible outcomes. Denotes the events in which both A and B have occurred. Hence, A and B denotes the simultaneously occurrence of the events A and B. Event A and B can be written as AB. And the probability of an event is obtained by using the properties of conditional probabilities. Like conditional probability is known as the possibility of an event or an outcome happening based on the existence of the previous event. As I have explained in this example, what was the previous event? What the previous event was drawing one card from the deck, that was queen. And then we had the probability that what is the probability that the second card would be jack. So conditioning it with Q, conditioning it with the queen, we got this answer. So, sorry, I would be rushing now. So this was the whole of the thing. Now this is the example of conditional probability in which a seminar class was there. And students in the seminar were asked about their gender and the carpooled, and this was the data that they got. Carpooled 9 males, and they didn't carpool was 31. And then we calculated the simple probability of conditioning probability, that is number of outcomes in A and B and number of outcomes in B. We are conditioning it with B, so it comes in the denominator. And we will find it with division as well, and it is 9 by 41. I'll also explain in today's class. This example I will also explain in today's class, so just skipping it very quickly. You have any queries, you can write it and you can ask me in the class. So coming to some recent updates, this was the probability that and we actually it is the normal life example that probability is apparently vague and defined as a favorable of all cases. I've already told you. And in a way, we can have probabilities in the clinical settings, and we can present it with values in terms of values P's and compared with alpha errors, and we can apply to diagnosis and treatments as well. And the current best practices for presenting probabilities in patient decision aids fundamental principles. So this is the article that shows that how probability can be applied in clinical settings. And there is this article shows that understanding how different numerical formats we can use it towards the particular opinions of deciding between probability format needs available for reviewing the bias in the decisions making for the patients or related to their outcomes in a specified time periods. So now MCQ session. So this is the first MCQ is what is the probability of getting an odd number in a dice when it is thrown? So it's very simple one. You can answer that. An odd number.
A.
Yes, A is the right answer. Here we use the sample size formula. The sample size formula was that we have 6 outcomes, and later on event E, we have 3 odd numbers, 3, and when we divide 3 by 6, we get 1 by 2. So it is a very simple calculation. The probability of getting 2 tails when 2 coins are tossed is when having a 2 tails using the sample space formula. I think this is a bit difficult. I will show it to you. The answer is D, 1 by 4. How it is 1 by 4? Like the sample space for having heads was 4, and the event E getting 2 tails was 1. So the probability of getting 2 tails was whole probability of all the events divided by the probability of that considered event. So it is 1 by 4. It's very simple. Next is what is the probability of losing a game if the winning probability is 0.3? What does that mean? What does that mean? I have told you that whenever we are considering the events, the sum comes up to be 1. Remember? So if the winning probability is 1, then the probability of losing would be, yes, it would be C, right? It would be C. Because when we say that this was an example of a complementary event. So probability of having the event and not having the event and equals 1. The product is 1. So 1 minus 0.3, it comes out 0.7. So what is the probability that we have a drawing an ace from a deck of 52 cards? Ace. How many aces do we have? Any guy? Yes. Okay, let's see the solution. So it's 1 by 3. As we have 4 aces and we have a deck of 52 cards. So it would be simple calculation of 1 by 13. So answer would be 1 by 13. Events which can occur together in probability theories are classified as, which can never occur together in probability theories are defined as. This is a simple one.
A.
Yes, mutually exclusive events. In a class 30, I have made it very easy for you. It's 6 by 20, 30% of the students have Urdu, 9 by 20, 45% have maths, and 3 by 20, 15% have both. If the student is randomly selected, what is the probability that he slash or, this slash is or, she study maths or Urdu? Please tell me which rule will be applied, either addition or multiplication. Either addition or multiplication. I will show you the calculation. Either addition or multiplication. It will be addition because we are using or. We are not
Addition.
using and. Yes. So for an or, it would be 9 by 20 because 9 by 20 was maths and 6 by 20 was Urdu, and both of them would be 3 by minusing both the probabilities 3 by 20. This one 15%, and then we get the answer, that is 3 by 5. So in a lottery, there are 10 prizes and 25 blanks. What is the probability of getting a prize when a lottery is drawn at random? We have 10 prize and 25 blankets. The probability of getting a prize. The answer is C. 10 by 10 by 25 total outcomes out of 10. The probability of getting prize out of all outcomes, that is 35. We have 2 by 7. So it's very simple calculation. In a box, there are 8 oranges, 7 white, 6 blue balls. If a ball is picked up randomly, what is the probability that it's neither orange nor blue? Neither orange nor blue. I think we will condition it. Nahin. Acha. We will use the sample space formula. We will use the sample space formula and the total sample space would be 21. And the event that the ball is drawn is neither orange nor blue, or the event that the drawn is white. Oh, they were indicating towards the white. Got it. So it would be 7 out of 21. It is 1 by 3. Okay. So last one is the probability of a sure event is. This is very simple. The probability of a sure event is equal to. Any guesses?
A.
Yes, 1. It's
1.
always 1. Yes. And last is in a special rule of addition of probability. I have given the probability formula. The events are always. Just look at the formula and tell me. I have given the formula. This is the probability of A or B, and we are adding the probabilities of probability A and probability B, and we are not subtracting any other combined probability. Then what type of event would it be?
Independent event. A.
Yes, it can be an independent event, but I could have removed this option. But choosing the best one, it would be mutually exclusive event. I will change this. Let me. Now your answer would be. Now tell me what would be your answer. If I change this upper option, dependent events.
B.
Yes,
B.
now it's B. So it's justified that it is B, mutually exclusive events, when you're not subtracting anything. So I have modified it. So this is the key. These are the references. And thank you so much. This is the YouTube link. I think there are no more questions. So we will end.
Thanks.
you so much,
presentation.
Dr. Amber.
And any questions we will address in the class. Thank you so much. Allah Hafiz.